Okay, so this is our second virtual SI session on October 1st. Yeah, and we'll just do a review of what our agenda is for today. We're going to be, so first few minutes we spent dealing with attendance, and then we'll go over a little bit of an introduction of the topics that we'll be covering today, and then we'll cover some example problems. At the end, if we have time, we'll go over any questions that you guys have. Anything to add to that, Josh?
No, just do want to reiterate that, these sessions are much more helpful and useful as you guys are participating, posting your questions in the chat. That way, because we already have a communication barrier because we're not physically with you guys. So definitely be involved, answer questions, or ask questions as well. If you have the answer to someone else's question, feel free to answer it yourself, but we'll try to get to all of them as well.
Okay, so before we move on to our examples, just going to do a quick review of Newton's law. So as you guys know, when you have forces, it's important to do free body diagrams, and it's also important to remember that the sum of all the forces is equal to the mass times acceleration. So that's something that's going to come up in our problems today because they're primarily dealing with forces. It's just important that we remember that before we start the problems. Yeah, anything else you want to review, Josh?
I think something that is important to remember is about specific kinds of forces, right? So with tension, so long as it is the same rope, or string, whatever cord, the tension is uniform along the entirety of that object. So make sure that I think we'll have a couple problems where we can address that again later. But just a brief reminder as part of the introduction that if you see us just label something as T rather than like T1 or T2, it's because the tension is uniform across the rope.
Okay, so yeah, we'll move on to our first example problem then. So for this first example, we have two blocks, one on a ramp and one attached to the end of a pulley. They are accelerating with the block on the ramp accelerating down the ramp, and we want to find that acceleration in terms of the variables m1, m2, theta, and g. So we're going to use our Newton's law and our free body diagrams to figure out what that would be and solve for it in terms of variables. And yeah, it looks like we have a question in the chat about your audio, Josh.
My audio?
Yeah. Do you see the question?
For sure. Let me see if I can. Okay. I'm using a headset. That's interesting. And my headset has been not working great recently. Let's see if this fixes it.
This might be the best we can do for now, and we'll have a look at it before the next session.
Can you guys hear me any better? Is this more clear? Yes, no?
I can hear you.
It is better?
Yeah. Okay. So getting back to the problem, what do you guys think the first step would be in this? Where would we start with this, as we know it's a force problem? You guys can just type it into the chat. Okay, so free body diagram. That looks like that was Joy's suggestion. And yeah, that's exactly where we would start with this. So, okay. I'm just going to draw it on here for now. So starting with box M1, it's on a slanted ramp. So I'm just going to draw the slant so that we take that into account. We have our normal force, which is perpendicular to the surface. We have our weight, which is always pointing downwards with gravity. this? We have the tension in the rope, which is pointing up the ramp. And for this example, the ramp is frictionless, so we don't have any friction force. Okay, so that would be our free body diagram for M1. And then for M2, we have the tension pointing upwards, and we have the weight pulling it down. That's for M2. Okay. Is there anything else that you think I need to add to these, Josh?
Well, for the weight for both of them, you just wrote it as mg. I think it would be more clear if you labeled what m, because the m's are not identical.
Right, yeah, that's a good point. When writing these free body diagrams, make sure that you label it M1 and M2 so you don't accidentally multiply by the wrong value. Okay, so I'm going to move these over to the whiteboard so that we can start working through the problem and writing out our Newton's law equations. So, sharing. Okay, so we have normal force, tension. Okay, so those are our two free body diagrams. And we're going to want to write out our equations for that. So using Newton's law, which is the sum of all forces equals ma, we can write out these equations. So we want to write out the forces in the direction that the acceleration is going. So for m1, that would mean that we would have we're using a tilted coordinate plane here. So rather than it being our standard plane, we have x in this direction and y in this direction to basically copy the slant of the ramp. So for the x direction for m1, we have the x component of the weight, which is mg sine of theta, m1g sine of theta. And we have the tension, which is going in the opposite direction, so we'll subtract that. And that is equal to m1 times the acceleration, just based on Newton's law. For our second block, we have the tension, which is pointing upwards, and we have our mass 2 times gravity in the opposite direction. So we subtract that, and we have m2 times a. So the question wanted us to solve for acceleration, and we have a there for both of them, but it wants it in terms of m1, g, and theta. So we need to eliminate that t for tension. As t is in both problems, we have a system of equations. We can just rearrange our variables and then solve for t and then plug that value into the other equation, which I will do right now. So
I have a question for you.
Yeah.
So why are the accelerations the same? Why is it not a1 and a2?
So in this problem, they're connected by a string over a pulley, meaning that they're moving together, and their acceleration would be the same in this case.
Okay.
Right. So we can therefore assume that a is just equal to a, and that's the same reason we can assume that t is equal to t instead of having t1, t2, a1, a2. So if I rearrange that first equation to solve for t, I get t is equal to m1g sine theta minus m1a. And then I can just plug that into the second equation, and I get m1g sine theta minus m1a minus m2g, sorry, equals m2a. So that's just me replacing the t value with what I solved for. Therefore, this problem is in terms of the variables that we want, but at the moment it's a little too messy. This wouldn't be a good way to answer the question. So what we're going to do is we're going to solve for a. So put all the variables on the same side that need to be there. So m1g sine theta stays here, minus m2g is equal to m2a plus m1a, which I'm going to move over to this side. Okay, final step. I can factor out this g here, and I can factor out the g's here. I can also factor out the a's on this side of the equation and divide the m1 and m2. So I have acceleration is equal to g times m1 sine theta minus m2 over m1 plus m2, because I can change it so that I have this side of the equation equal to m1 plus m2. So I can divide by that. So that would be my final answer. That would be how I solved for acceleration in terms of variables. Okay. Do you have anything to add to that, Josh? Okay. Any questions on that before we move on to the next one? Okay. So if everybody's on the same page here, we'll move on to the next example. Okay, so example 2 is very similar. We have the same kind of ramp system. The only difference is that we're including friction in this problem. So, and we're also going to be calculating this in terms of numbers and values instead of variables. So taking what we had from the last one, we have acceleration is equal to m1 sine theta minus m2 times g over m1 plus m2. And just take a minute to look at that and see if you can figure out where we would add friction into that problem. So let's start by looking at the frictional force. So we have the frictional force is equal to 0.1 times the normal force. That's the information that's been given. Now, if the normal force is pointing upwards from the box like this, and we have gravity pointing downwards, looking, hi, I can hear you now. Were you?
Yeah, sorry everyone. Yeah, the campus Wi-Fi booted me, so I had to reconnect.
Okay, so we're just going over the second example and including friction at the moment. So looking at, we want to solve for the normal force in terms of the variables that we have. So we know using Newton's equation that the normal force minus m1g cosine theta is equal to m1a. Acceleration in the y direction, which is 0. So this whole thing is 0. So the normal force minus the weight component, y component, which is the cosine theta, is equal to 0. Therefore, the normal force is equal to m1g cosine theta. Now, as we can now replace that, the frictional force is equal to 0.1 times m1g cosine theta. So going back to our original equation for acceleration, we can see that the forces are all on top while the masses are on the bottom. Now, the mass didn't change, so we can leave the bottom of that equation alone, but we do need to include our frictional force. So that now gives us acceleration is equal to m1 sine theta minus m2 minus 0.1 times m1 cosine theta from the friction. And then that's all still multiplied by g over m1 plus m2. So all we did in this was take our original equation and just add the frictional force to it, or subtract in this case, because friction tends to move opposite to the direction of acceleration. Okay, before we start plugging in values, is there anything you want to add to this, Josh?
No, I mean, it looks pretty good to me. I have nothing to add. Does anyone have any questions about how we got to this value? I'll take that as a no.
Okay, I'm going to open up the whiteboard now so that we can continue the work. Okay, so our equation that we just calculated was that the acceleration is equal to g times m1 sine theta minus m2 minus 0.1 times m1 cosine theta over m1 plus m2. And the information we were given is that m1 is equal to 15 kilograms, m2 is equal to 10 kilograms, theta is equal to 60 degrees, and g is equal to 9.80 meters per second squared. And now, as we have it in terms of those variables anyway, all we have to do is plug it in. So we have acceleration is equal to 9.80 times 15 sine 60 degrees minus 10 minus 0.1 times 15 times cosine 60. And that is all over 15 plus 10. So I just plugged in the values that we had into the variables from the equation before. And if you put that all into a calculator, you get an acceleration of 0.878 meters per second squared. And that will be your final answer.
Do we have any questions about that? I know the last step was basically just plug it in, but anyone get lost, anyone need any clarification?
Okay, so you're asking why is it cosine and not sine? So that cosine value is for the friction. The friction is equal to 0.1 times the normal force, right? That was given. So as it's equal to 0.1 times the normal force is in the y direction, which is the cosine, whereas the other forces like tension and gravity, and weight, for instance, were in the x direction, which is sine. So as we were looking at the y direction, we use cosine.
So I believe in the chat, did you need to write mu f norm? Because if that's the case, then that's actually from the next section of the textbook, which has not been covered in lecture yet. In which case, that's why we've just simplified it to just giving you a certain value for it. Technically, yes, but
Yes.
you are correct. The mu would be the 0.1. But again, because you haven't been taught that, we just gave that to you as a proportion rather than like saying, oh, mu is 0.1, because then people might get confused and be like, oh, what's that? But yeah.
Okay, so it wouldn't be sine theta because for instance, if I draw out our force diagram again, we have mg pointing downwards and the normal force pointing upwards. So the normal force is equal to this line right here. And theta is right here. So the normal force is equal to mg cosine of theta.
Does that clarify it for you? I will say that it does, tilting the axis does make your math tend to be easier. However, it can lead to some conceptual confusion if you don't do it correctly. So it's definitely something that you do. You have to make sure you practice and understand. Cosine isn't necessarily for the x direction. So the question, or what someone said was that cosine was for the x direction. It's not. That's how it tends to be, because that's just how, if you use a normal axes with y directly up and x directly right, that's how it usually ends up being. However, cosine is just a trigonometric value. Yeah, and so yeah, cosine, like you just said, is adjacent over hypotenuse, right? So it's not necessarily guaranteed x. It's just you have to make sure you study the diagram. That's why we always make sure we have diagrams for these so that we're able to visually understand them. Good question, though.
Yeah, it's very good. It's important to pay attention to what direction the forces are going in so that you make sure that you use the right trigonometry. Otherwise, that can mess up your answers. So it's definitely a good thing to pay attention to.
It is now 12:30, which means we will move on to our challenge problem.
Okay.
So if you guys can turn there on the PowerPoint, it says two blocks are connected by a cord that is passing over a frictionless pulley, and those blocks are resting on frictionless planes. So there is no friction in this problem whatsoever. So we can just forget about that for now. So we're asked which way will the system move when the blocks are released from rest. So initially, the blocks are being held where they are. And so what we want to find is when they are let go, which direction do the blocks accelerate? And then part B is asking, what is that acceleration? So those are kind of tied together. Part C is asking, what is the tension in the cord? And as you will find out, once we have our answers for A and B, finding C is fairly easy. If we go to the next slide, we have the actual given values for the masses of each block and the angles of our ramp.
Yeah, so the questions were like first, which way will the system move when the blocks are released from rest? What is the acceleration and what is the tension? And we will use these values for this problem to solve that. It's very similar to the previous one where you're going to want to solve in terms of variables first and then plug in your numbers. Yeah, so we'll start with our free body diagrams. So just going to call this block A and this one B.
Well, they're currently labeled M1 and M2.
Oh,
might be confusing.
Yeah. Sorry, didn't see that. Yeah, so M1 and M2. So for the free body diagram for M1, we have the normal force, we have the weight, which is M1G, and we have the tension up the ramp. Okay, and that's for M1. For M2, we have a similar one, but in a different direction. We have the tension up the ramp, the normal force, and the weight. Okay, so again, doing the similar thing to what we did in part one of the first problem, we're going to write out our Newton's law equations. So for M1, we have the tension minus M1G sine of theta again. So it's our x component is equal to M1 times A. And again, we can assume that A is consistent for both of them because they're connected by rope, so they're moving together.
Freya?
Yeah.
Well, A is constant for both of them. In this problem, the difference between this one and the last ones is theta is not constant for both of them. So if we're writing in variable form, we should probably write that as theta 1.
Yeah, that's definitely true. Pay special attention to your notation with these kinds of problems because theta is changing. So theta 1 for that. And then looking at our second one, we end up with M2G sine theta minus T is equal to sine theta 2, sorry, is equal to M2 times A. Okay.
I think it would be helpful for clarification because we have different angles. If you drew in on the diagrams where those angles are.
Oh, okay. Yeah, that's an important detail. So for the first diagram, theta is here.
Theta 1?
Theta 1, yeah. And for the second diagram, we have theta 2. Okay.
All right, so we now have all the equations that we need from our diagrams. And so what we're trying to find is which direction it will accelerate, whether it will go up the ramp or down the ramp. And so one way that we could, I mean, if you think about it, you look at both of our equations, the acceleration is on the right side. So, I mean, you could divide by m1, right, or m2. It's not super necessary at the moment. But you'll find that, go ahead and write on this as well. Right. Blue? What is this? What's blue? I don't want blue. That's too similar. Right. If this t is larger than this, then it will give you a positive value, which means you'll have a positive acceleration. Whereas, but if the other way around, if the t is smaller than this value, we'll have a negative acceleration. So, Freya, which direction did we assume to be positive?
We assumed the right block moving down the ramp to be positive.
Okay.
I believe.
So I'll go ahead and draw that in. So this is positive. This looks like an X. Positive acceleration. So if we get a negative value for the acceleration, what we know is that it actually just moves in the opposite direction as we assume. But for now, we can just pick a direction and assume that that's the direction it's going to go until we're proven wrong. If we're proven wrong. Yeah.
Okay. So as we know that, so if we take these equations, we can then solve for acceleration. I will move these over to the whiteboard so that we have more space to work. Okay.
So while you're doing that, Freya, I'll answer the question. Someone asked why theta is different on the free body diagrams. Well, if you look at the ramp that we have here, and you compare it to the ramps from the previous problems, before it was a right triangle. And so the only theta that we really had to worry about was the incline of that ramp. However, this is now not a right triangle. I mean, you can look at it as if it were two right triangles but next to each other. And because we have those two right triangles, we have two thetas. The incline angle is different for each of the blocks. So you have to make sure that you include the different angles in each of the diagrams. Does that answer your question?
Okay.
You can go ahead and keep going for it.
Oh, so like where theta is on the free body diagram? Because it appears kind of in different places.
Oh, got it. It's I mean, if you think about it, like I said, if you think about it in right triangles, if you cut it right, I guess it's technically not in half. If you cut it vertically, where the two right triangles are together, then you see that the it's like, here, let me just draw it. Where's there. So if we have two right triangles, we have one like this, and we have one like this. Okay, I'm trying to draw with the trackpad. This is not working. But so because the reason that it's on different sides is because the theta is on different sides. So we have theta 1 is on this side, theta 2 is on this side, right? So that's why that the direction is different. I'm gonna go ahead and erase this.
Okay.
All right, let's go ahead and plug in our values, right?
So Yeah, so for this, just like in problem 1, we're not going to want tension in here necessarily because we don't actually have a value for tension. So what we're going to want to do is eliminate that tension, same way we did in problem 1, solve for it. So we have T is equal to M1A plus M1G sine theta 1. And then we're just going to want to plug that into the second one. So we have M2G sine theta 2 minus, make sure you add the negative sign to both. You have M1A minus M1G sine theta 1. And that is equal to M1A. So again, just put all the like variables together, and we end up with M2G sine theta 2 minus M1G sine theta 1 is equal to M1A plus, sorry, this is M2A plus M2A. Okay. Again, factor it out so you have A times M1 plus M2. And then you divide the M1 plus M2. You can factor out the G, and you get acceleration is equal to M2 sine theta minus M1 sine theta times G.
1, right?
Sine theta 2, sorry, theta 1. Gotta keep remembering that. Over M1 plus M2. And that is your acceleration. So if we take the values that we were given, we know that M1 equals 100 kilograms. M2 equals 50. Theta 1 is equal to 30 degrees. Theta 2 is equal to 53.1. So those were what we were given. You just plug those in. You get acceleration is equal to 50 times the sine of 53.1 minus 100 times the sine of 30, times gravity, which we know is 9.80, and then we add that to 50, we divide that by 50 plus 100. And if you plug all of that in, you get an acceleration value of negative 0.65 meters per second squared. Okay, so going back to the problem, we said that if the right block was moving down the ramp, that would be a positive acceleration. However, we got a negative value. Therefore, we know that the left block is moving down the ramp, and that's the direction of the acceleration.
So to answer part A of our problem is when the blocks are released from rest, which direction we know that block 1 will slide down the ramp and block 2 will slide up the ramp, opposite the direction of our initially assumed acceleration. Does that make sense to everyone?
So yeah, from our math, we're able to figure out that the direction of acceleration is this way. And that it was equal to negative 0.65 meters per second squared.
Right, and that's our answer for part B. Is technically the negative applies to the direction. So our actual answer for part B would just be 0.65. 0.65 meters per second squared. And part A would be our answer for the direction. Just say that it moves to the left. Now,
right, so that would be 0.65.
Part C. If you go back to the whiteboard, does it still have the stuff that you wrote down?
Let me check. So, no, it does not, but I have all the equations. So we have acceleration is equal to negative 0.65 meters per second squared for this. And then going back to an equation that we can use, for instance, we have our two equations, which are t minus m1g sine theta 1 equals m1a. We don't even really need to use the second one because these are all variables we have. We know what m1 is equal to, we know what gravity is, and we know what theta 1 is equal to, and we've just calculated acceleration. So if we plug all of that in, we can solve for tension.
We also remember that another reason we don't need the second equation is because, as we've said in the beginning, the tension is equivalent. So the second equation is technically the tension on the part that's connected to M2, but we can just assume it's the same as the tension connected to part 1 or block 1, so we can just only use this equation. We don't need to bother using both of them or solving for the system. We can just solve for T.
Okay, so we have m1 theta 1, and we just calculated for acceleration. So if we plug that in, we get t minus 100 times 9.8 times sine of 30 is equal to 100 times negative 0.65. So plugging that into the calculator, we get it. $425 newtons. That is our value for tension.
Well, let's think about that quantitatively. Does that value make sense? If we go back and look at the slides, we have the masses are 100 kilograms and 50 kilograms, right? And so the respective weights, if you multiply those by the gravity, is 980, and then what's that, 490, right? So, and those are just straight down, and so the tension would need to be somewhat of a similar magnitude. So if we had like a tension value of like 25, right, then we'd probably be like, something's up there because we have the weight values are much larger. But because 425 is right up there as far as the large numbers go, we can assume that we've gotten a pretty close answer. That's a general way that you guys can approach problems on the test. So it's always good to be like, okay, I got an answer, but does this answer make any sense at all? Like if you find that the initial speed of the projectile is 2 times the speed of light, it's probably something went off there. But so it's always a good idea to go back and think logically, does this answer make sense? All right, well, it is 12:50, so according to our agenda, it is now time for our closing questions. Does anyone have any questions regarding either the problems we did, anything as far as just concepts from the class, anything about tension? I know I've had a lot of people ask me questions about tension during class in my sessions, and I know it can be a bit confusing, but I don't know if you guys have any questions, go ahead and post them into the chat room and we'll try to address them. So I'm going to assume that either people are still typing their questions or you guys are all masters of stuff. And you guys all got 100% on the midterm that you just had, right? That's probably what happened. So you guys should, so I was thinking the next virtual session, you guys could teach us. No, I'm just kidding. Okay, cool, we have a question. Can you refresh how we know if it is T minus or minus T? Oh, you're talking about in the, right, in our equations where we had T minus M1G sine theta 1. Right, so it really comes down to how, it doesn't have to be, there's not really a one answer for that. It doesn't have to be T minus 1 minus T. It comes down to how you personally define your axes. Because we defined the positive direction as M1 sliding up the ramp, we had that the positive x direction is where T is. So we make T be positive, so it's T minus the 100 or the M1G sine theta. If we had defined that the negative direction was that way, then we would have a negative T. Did you have anything you wanted to add about that, Freya?
I'm just drawing it out a little bit. So if you have T going in a certain direction, it all depends on what you define as positive. So if I'm saying up the ramp is positive, down the ramp is negative, then I would have something like this. However, if I said that down the ramp was positive and up the right was negative, then then it's more like that. So it's really dependent on what I define as positive and negative. And that's how we came up with it today.
Right. So someone asked is when the next virtual session is. We have it planned to do it, yeah, as you said, on October 15th, 2 weeks from now. I encourage you guys all to attend because that would be, I believe, almost exactly 2 weeks before your midterm. Does that mean we might have a session the day before the midterm? Now I think about that, because that'll be what, 10/29, and your midterm's the 30th. That's cool. Yeah, so I think we should, in theory, have 2 more virtual sessions before the midterm.
Yeah, and in the chat, so there were 2. So to follow up on the question about negative or positive T, it says, so it depends on which direction the objects will move when released from rest. So you don't necessarily have to define positive as the direction in which it moves, but that is something that is often done because it makes the problem a little easier. So a lot of times people will define the positive direction as the direction in which the object moves. And another question is it possible to have 3 SI sessions before the midterm? And yes, it's definitely possible. We each have 2 sessions a week in addition to the virtual ones every other week. So it's definitely possible to attend 3.
And someone asked if one attends all 3 virtual SI sessions, do they get extra credit? That is technically correct. Yes, you will get each attendance that we have recorded of you guys being here counts towards your total. And technically there will be 3 before the midterm. However, there are a lot of benefits of going to the in-person sessions that we are not able to factor into the virtual ones. Virtual ones are great because they are accessible and easy to go to. I know for people who commute, it can be a pain to have to come to campus. But at the same time, you're not able to get that same kind of, not so much one-on-one, but individual help as you do in the in-person sessions. So yeah, you can meet your requirement just virtually. I would still recommend. You'll probably get just as much, if not more, understanding of the material in the in-person sessions as you get from these virtual ones. All right, any other questions before we close out? We'll give you guys another minute to post your questions. And in the meantime, I will give us our closing things. Right, so this has been virtual SI session for Phys50 is October 1st. And we covered a lot of ramp and pulley problems. You guys will probably encounter those decent amount in this class. I believe the next stuff that we will talk about is going further into friction. There's different kinds of friction, both friction when you're moving and friction when you're not. And so that's what we'll encounter next. Probably be going over that in some of the in-person sessions this next week. Yeah. All right. So we have no more questions, looks like. So we'll go ahead and wrap it up. Thank you guys for coming. Thanks for participating. Thanks for asking questions. And yeah, we will see you guys tomorrow.
Yeah, we'll see you tomorrow.